think we are ready now, so all the committee members are. So, goedemorgen, good morning and welcome to the Faculty of Aerospace Engineering. My name is Marilena Pavel and I'm going to chair this session. We have a new group, Design Synthesis Exercise, and their work was on medium altitude, long endurance, observatory aircraft for climate research. The procedure is as follows. We are going to have 20-25 minutes presentation. Afterwards, we have time for some questions, about 10-15 minutes. And afterwards, there will be a ceremony for diploma. And my colleague Fei Jiayin, the tutor of this group, will hand in the diplomas. So lots of success.
Okay, welcome everyone. Thank you everyone for being here. It's a bit warm today. Sadly, this is not a one-time event. We are now living through a whole heat wave and an unprecedented one. But luckily, this ties well with the topic we're going to speak about today. I'm Davide, and together with my colleagues Diogo and Walter, we're going to explain our design on SORA, a stratospheric observatory research aircraft. Today, we're going to start with a bit of background information, make sure everybody's on the same page. Then we're going to explore the why we did this. Then we're going to dive deep into the how we did it, exploring our design. Have a summary at the end, make sure nobody got lost during the presentation. And then we're going to show some conclusion and recommendation for future work. As mentioned before, we have a Q&A session at the end. So if you have any questions, note them down, and we can then address them later. So I wanted to address the team sitting in the first row. Wouldn't be possible without you. So let's start with some information. Some of you might have already seen this graph, but for the one who never saw it before, it shows the global temperature anomaly over the past 160 years, and with a special increase over the past 6 years or so. And there is no trend of this going down. This has a really big impact on climate, rising sea levels, habitat disruption, wildfires, food scarcity, and also abnormal weather events like the one we are experiencing right now. Aviation plays a really big role in this. 3% of CO2 emissions come from aviation, and 4% of global emissions come from aviation. And this is not just CO2 emissions, but it's pollution delivered at high altitude, also of carbon monoxide, sulfur dioxide, methane, nitrous oxides, and contrails, the white lines we see here on a nice clear day. And this happens because a conventional jet aircraft dumps 8.5 tons of CO2 per hour of flight. And as I said before, it's not only CO2, but it's also leftover from combustions, particulate matter, in which water vapor can then condense and form this long-lasting contrail, which when multiple line up in the sky, they affect the radiation balance of the Earth, increasing the greenhouse effect by trapping infrared radiation. So we started looking into this and we need to help develop better ways of tracking how the climate is evolving. This is a really important thing. We're now setting a lot of new regulations, new standards to have more efficient planes, but can we see an actual impact on the climate? That's why we saw that there is a market need for better climate models, and they need a high-resolution validation data. Right now, models operate with a resolution of 100 by 100 by 100 kilometer cubes. And then they apply dynamical downscaling to go into more detail and actually more useful data. All of these need high-resolution data for it to be effective. We also saw a need for real-time climate monitoring, being able to analyze the pollutant coming directly after an aircraft, and also looking at the pollution over city, how it develops due to the changing climate and also due to different winds. So we looked what is currently available in this market. We know there are satellites. They have really good global coverage. They orbit high around the Earth, but they have a bit lower vertical resolution than what is needed for some models. There are weather balloons. They have really good vertical resolution, but they have low controllability. They just get drifted around by the wind. There are conventional aircraft. They have a really good global coverage, but they're a bit expensive to operate, and they have a short endurance. They can fly for maybe max 18 hours, but if you want to sample over 2 months, well, then you run in difficulties. And then there are drones. They're really flexible, but they come with a bit limited payload capacity. So with all those ideas in mind, we looked what's missing. And this is why we developed SORA, our stratospheric observatory research aircraft. And as a fun fact, it means sky in Japanese, which fits well with some of the parameters of this aircraft. It's a 36-meter wingspan, solar-powered, fully electric plane. It's going to be uncrewed due to the length of the mission, as I mentioned, 60 days. And wherever possible, we made sustainable design choices to make sure our aircraft wouldn't contribute to the global warming of Earth. Its goal is to perform atmospheric measurements at an altitude range from 15 to 25 kilometers, and as much global coverage as possible. Due to our long endurance, we could even circumnavigate the Earth 4.5 times in one mission duration. Global coverage, it was really important for us to do. Of course, we are solar powered, so we have some limitations. We're going to explore them a bit further down in the presentation. So with this, we came up with our mission, and it is to design a high altitude, long endurance platform to measure atmospheric composition, aircraft cruise emission, and contrast for live climate monitoring and research. Now, Diego is going to explain a bit more how we did this, and I'll go over our design.
Thank you, Davide. So now that you got to know the motivation behind this project, I would like to present to you our final product and tell you more about it. SORA will have a 36-meter wingspan, which is roughly the same length as 3 buses stacked end-to-end. Its fuselage length will be 12 meters, and it will weigh 218.5 kilos, which is roughly the same weight as a motorcycle like the one that you can see there in the picture. Now let's move on to the actual parts that made this design come to life. Starting with the payload instruments. The payload instruments that SORA will carry are all of the ones that you can see there. To measure pressure, temperature, and humidity, we will use one single instrument, the radio sonde DFM-17. Then, in order to measure atmospheric composition, we are focusing on the use of spectrometers, which are kind of like cameras, except they are able to see in a wider wavelength range, ensuring that we can capture the full absorption spectrum of all of the gases we are targeting. In order to detect the gases that are too rare to detect with our spectrometers, we are going to also have an air sampler that takes raw samples of the air, and they can later be analyzed in laboratory. In order to understand the impact of contrails on Earth's radiation balance, we are using 2 sensors. One to capture incoming shortwave solar radiation, and one to capture outgoing infrared radiation emitted by the Earth. Then, finally, we will also include a LiDAR system in our payload instruments to get information about the contrails, like their thickness, their altitude, and the ice particles concentration, and even some information about about aerosols atmospheric composition, which can be then supplemented by our in situ aerosol sensor. These payload instruments, of course, they produce lots of very useful data, but we need to be able to transmit that data to the ground somehow. For that, our aircraft will carry satellite-based communication systems that ensure beyond line of sight communication. These systems will be able to then transmit live telemetry data and the data from the payload instruments. We'll use 2 systems. Firstly, a Starlink mini terminal for high bandwidth data transmission and for handling of ground station commands. And for redundancy regarding ground station commands, we also have an Iridium terminal. I'd like now to move on to the body of the aircraft and start with the fuselage. The fuselage will need to be able to support the payload at the nose, the wing, and the tail at the back. It will have a tapered cylindrical shape, as you can see there in the picture, which is useful to save weight, and it will be fully made of galvorn, a material made on carbon nanotube, based on carbon nanotube technology, which has a big advantage for our design because it achieves strength properties very close to traditional carbon fiber reinforced polymer while being 100% recyclable without losing fiber strength. Then, moving on, and let's focus on the most important part of any aircraft, the wing. The wing was designed on 2 perspectives, aerodynamics and structures. On the aerodynamic side, the goal is to ensure that the wing produces as little drag as possible, while, of course, being suited for the long endurance mission of our aircraft. For this, we'll use the MH114 airfoil, which is especially designed for long endurance operations at the low Reynolds number that our aircraft will be flying at. Then, on the full wing configuration, it will be tapered, which means that the tip chord is slightly smaller than the root chord, as you can see there, and this is very useful because it reduces lift-induced drag. On the structural side, the wing will need to be able to support loads like torsion, bending, and shear, and for that we will use one single cylindrical spar positioned in the wing, as you can see there. This spar will carry all of the main primary loads, and it will be made of galvan, just like the fuselage. And then, to be able to hold the aerodynamic shape of the wing, we are also going to have a total of 84 carbon fiber reinforced polymer honeycomb ribs, which are placed across the span of the wing. And of course, the wing skin itself is also very important, and that will be made of thin mylar film. The top of the wing is fitted with solar panels for solar power generation. And these solar panels power the aircraft subsystems during the day, and they also charge batteries which enable overnight operation. These batteries are stored inside the wing spar, and they are designed to be removable, such that once their capacity degrades, we can simply replace them and continue on with the operations of our aircraft. In the wing, we are also going to have the engines that make this aircraft able to fly, and we are going to have 4 engines, 2 on each side. These engines are electrically powered, and they have 2 blades each, which is a configuration highly suitable for aircraft that fly at high altitudes. The engines were sized in terms of their radius and their rotations per minute in order to ensure they are as light as possible while fulfilling all the operational needs of our aircraft. Finally, at the back, we are going to have a V-tail to ensure controllability and stability of this aircraft, which has an advantage compared to traditional tail configurations due to the lower number of fuselage interactions. The V-tail is going to have rudder elevators on its edge, which allow us to pitch the aircraft and also to yaw. And then on the trailing edge of the wing, we have ailerons, which allow the aircraft to roll. Now that you got to know our design, I would like to tell you more about the operations of this aircraft, because surely you might be wondering where can we actually operate, considering that solar power is not available everywhere at the same time. Indeed, solar power is the main constraint of the operations of this aircraft, because of course during the summer, for example in Europe, we have lots of solar power. During the winter, not so much, and this varies depending on where on planet Earth we are. For this, and in order to ensure that our aircraft comes as close as possible to full global coverage, we needed to design an operational profile that is as energy efficient as possible. And that operational profile looks something like this. During the day, the aircraft will cruise at its assigned altitude, collect all of the scientific measurements, and operate as normal. Then, during the night, when the sun goes down, we have the possibility of performing a controlled power-saving descent, which is good for energy-saving purposes, down to its lowest operational altitude of 15 kilometers. It will spend there flying during the night, and then in the morning, once we get solar power back up, we can climb to the altitude that we desire. Following this operational profile gives us the possibility of extending the geographical range further than what would be possible if we simply were to fly at the same cruise altitude for 24 hours straight. This operational profile then tells us where we can operate and when, and it looks something like this. On this axis, you can see the months of the year, and on the other axis, you can see the latitudes on planet Earth. And these numbers here showcase you the minimum top cruise altitude that our aircraft is able to fly at. So, for example, if we focus on the summer months, and in Europe, which are those latitudes around 40 to 60 degrees, we can see that our aircraft is able to just continuously fly at 15 kilometers, and there is no need to even perform the power-saving descent. But if we focus on the same latitudes, and we go to the fall months, you can see that the minimum altitude goes to 18 or 22 kilometers. This means that during the day, we cannot fly lower than those altitudes, such that then you can perform the controlled power-saving descent down to 15 kilometers where you fly at during the night. And now that you got to know the design of Sora and a bit about how we plan to operate these aircraft, I'm going to hand it over to Walter, who will give you a quick recap, as well as some of our reflections and recommendations from working on this project.
Thank you, Diogo. So far we've covered what we did and why we did it. I'd also like to take a look with you at the future of Sora, but first let's do a quick recap. Sora can cruise at a maximum altitude of 25 kilometers for a full 60 days. Sora carries a scientific payload meant to do measurements in the atmosphere. Sensitive instruments are placed in a heated and pressurized compartment. Communications are handled via a Starlink terminal using low Earth orbit satellites. A V-tail ensures controllability and stability, with the added advantage that it's also more efficient than a conventional tail. Propulsion is covered by 4 electric motors, each powering a 2-bladed propeller. For propulsion, you need power, and Sora can generate her own power. We use solar panels placed on the top of the wing surface to generate this power, and whenever we generate excess power, we can store it in the batteries, which are then in turn stored in the wing. We can then access this power when we need it, such as during dawn-dusk, but also night or any expedited climb maneuvers. So far, we've shown that Sora can exist on paper. However, for this aircraft to fly in the real world, more work is needed. Let's look ahead at the recommendations for future design efforts, the external challenges Sora faces, and Sora's future in general. So, everything we've showed you today was based on analysis where we used models. And these models were kept deliberately simple for a specific reason, to get us to a converged design within the DSE timeframe. But this means there's room for improvement. We could use higher fidelity models for a specific purpose, to reduce uncertainty in our estimations and to capture physical phenomena that our current models simply cannot represent. Examples of such models are finite element methods or computational fluid dynamics. The result is a more trustworthy number rather than just a coarse estimate wrapped in conservative margin. I would also like to touch upon the solar model. The current model we use uses flat surfaces parallel to the surface of the Earth. However, in reality, the wing deforms and twists. Thus, to ensure a full 60-day cruise mission, we need to do full mission simulations, taking into account the actual deformed geometry and orientation of the aircraft. This also means taking into account the change in solar declination over 2 months. It means modeling battery cycles and the degradation, and as well station keeping against winds aloft. Because this ensures that the future simulations are more accurate than our current simulations, which only cover a 24-hour window. Altogether, we could get a more genuine picture of where Sora can operate and what kinds of missions are possible. However, let's now take a step back from the details and take a look at what continuing a project like this could look like in the future. We have divided the post-DSE time in a couple of phases, starting with finishing a detailed design and a critical design review. Then procurement of materials and manufacturing of parts, followed by assembly and integration, and then an extensive test campaign running all the way from component level tests to full flight tests. And finally, certification and deployment. I think this nicely shows the distance from a design that can work on paper to something that actually flies in the real world. However, there's another dimension to it, because getting there takes more than just designing and building the aircraft. Sora shows what a future high-altitude, long-endurance solar unmanned UAV could do. However, for this unique category of aircraft to really thrive, the world around it needs to be ready to support it. And we've identified 3 recommendations, the first of which is the technology. Sora relies on future battery and solar cell technology that is close, but not here yet. So once research institutes and manufacturers mature this technology, and perhaps more importantly, prove its viability in real-world conditions, Sora's 60-day endurance stops being a projection and starts becoming reality. Secondly, standardizing the data. As Davide told you, current climate models use very coarse resolution, and furthermore, there's no shared standard on how to use data. Once the scientific community adopts standardized ways of including data sets as validation for their models, SORA's high-resolution data can start immediately making the difference for the climate models that matter. And lastly is the airspace. SORA's 60-day mission means that she might well cross into many countries during this time, and currently crossing borders means crossing regulations. So once high-altitude, long-endurance unmanned aircraft regulations are standardized across the world, SORA can fly a truly international mission profile instead of the ones restricted by the borders of national airspace. Altogether, SORA could get another step closer once these recommendations are met to becoming a real usable platform to deliver meaningful data. And this brings me back to why we are doing this in the first place. We know surprisingly little about what is happening right above our heads. We look up at the sky and see a clear sky, but we cannot yet see how we are changing it. SORA is one piece of the puzzle, a way to start building that picture. Thank you.
So thank you very much. I invite the group here for the questions. May I have the...
Yes.
So we have enough time for questions. Do we need some light so that we can see from where the questions come? May I ask you the first question? What are the competitors on the market with this kind of, I mean, what are, do they exist or you are the first one?
Yeah, I think I can take this question. So, according to our research, we have satellite as suggested in the slides, and we have some similar aircrafts like Airbus Zephyr, but you know, aircraft Zephyr is only 75 kilograms of mass, and we have 218 kilograms of mass, so we can carry out more mission, and this can make our product more competitive. I hope this answers your question.
Okay, thank you. So I will go first to the jury members. Actually, you know, you ask the question and then they repeat it for online, because otherwise we move all the time with the mic.
Yeah, we have some experience with this. So, why did you go for Galvorn?
Okay.
Why Galvorn? Who has?
The question is, why did we choose for Galvorn for the structure of the aircraft? I think Eve can best answer this.
Yeah, so we chose Galvorn. We considered a lot of different like high strength, low mass materials. So we looked first at aluminum was like immediately discarded because it's just too heavy for this type of high altitude UAV. Then we looked at CFRP, but we had a lot of requirements on sustainability and recyclability. And CFRP, which is carbon fiber reinforced polymer, is not generally recyclable, or at least not easily recyclable. So then we looked at carbon reinforced thermoplastic polymers, which are recyclable, but you lose a lot of fiber quality when you do the recycling process. So then we took a look at some novel materials, and Galvorn came across. And so this one is a carbon nanotube reinforced polymer. And when you recycle it with a thermoplastic polymer, it is fully recyclable with no degradation in quality. And it also has very good performance. It has super high tensile strength. I think it's 15 times stronger than steel, and it weighs 40% of what aluminum would weigh. So does that answer? Huh?
It's expensive.
Yes, that's true.
Comma, and that's where my problem starts.
That is true.
Yeah.
Yeah, that it is very expensive, but because it's a novel material, we expect the
Okay,
technology.
I'll buy it's expensive, but you're also heading for certification.
Yes.
It's not yet certified.
No, indeed.
So you got a big problem.
But this is again where we're looking into the future. We looked at future solar technology.
Excellent answer.
Yeah.
But what I'm referring to is you're taking quite a risk here. Are you willing to take that risk? Obviously you do. You did consider this risk. So somebody might pop up and say, who's going to pay for that and who's going to certify? On the other hand, what kind of a mission are you flying? Is it a commercial mission?
No, it's like a private, I think.
It's a scientific
Yes.
mission, which does not necessarily need certification.
Yes, exactly. It's very.
So why do you certify them?
So why do we certify our plane? I think again, this is something where it's a lot of future technology, like it hasn't really become very mature, this sort of sector as well. So we're looking into the future, and it's hard to say how it's going to look at the moment.
Yeah, but the answer is you're looking for a specific market as well, because if it's certified, it's easier to enter other nations or other
Indeed, yeah.
areas of airspace.
Yeah, that's true.
That's easier. So it's implicitly it's a good answer. But there's some, it's risk taking on your side as well. Okay, thank you.
Yeah.
For your design process, first question, what are the design requirements of this aircraft?
Okay. So the question was, what are the design requirements on this aircraft?
What did you start out with?
Yeah, what we started out with. Do you want to answer? With the.
I can answer.
Yeah, sure.
So we started with the most important requirements are that the aircraft should be capable on flying at up to 25 kilometers and having an endurance of 60 days, including that it should be zero emission. I think that are the major requirements of our aircraft.
40%.
And 40% recyclable, yeah.
Okay. Then it might not be you, it might be your sponsor that makes me wonder. Your bottom altitude, operating altitude is 15 kilometers?
Yes, yeah.
What are you going to do to controls?
Uh,
Because they're not there.
No, but we are measuring them from upside. So we fly above them, and the higher we fly, the less resolution the controls will have. So that's some kind of trade-off you can do, flying lower with a lower range of controls, but have a higher resolution, or flying higher with less resolution.
Yes, please. Thank you for the nice explanation of your final product and the mission. How will the vehicle get to the altitude?
So the question is, how will the vehicle go to the altitude? Yeah, correct.
Yeah. So so the idea is, and that's based on what's being done today for such missions, because there are no clear regulations yet for high altitude, long endurance missions. The idea is that we get, with cooperation with the air traffic management, we get a segregated airspace that's probably cylindrical in shape. For example, for Zephyr, I found a document that says that they use multiple such airspaces that are timed to the climb, and they just climb there making circles for the whole day, because the idea is that you start when the air is also still, so in the dawn, and then you take off. You climb during the day to maximize the use of the solar power, of course with fully charged batteries, and then you climb above the general air traffic, so like flight level 510. Yeah, and then for the descent it's similar, but it probably happens at night, because then you can land just at dawn again, so that you have visibility for the ground crew, but it's also the air is still again, which is really important, because with such an aircraft optimized for a very high flight with really long wingspan, it's all very susceptible to turbulence.
But it will climb on its own power to the altitude.
Yeah, and we think that's possible.
Okay. Some other questions? Public, yes, please.
Well, part of the journey there.
Okay.
Just didn't answer. And a question about the altitude as well. So you said you want to know more about the climate, and of course there is a lot happening between 0 and 50 kilometers. A lot of, or most what happens is below 5 kilometers. I was wondering, how did you come up that this actual height is relevant, and how much would that percentually improve the data we have today on the different items that describe the climate of the different regions that you will be flying?
Okay, yeah, so the question, if I understood correctly, is how did we decide for this altitude and what to measure, taking into account that most of those things are actually below those altitudes? Yeah, is that right?
Yes, I can answer this. For now, a lot of the climate models are using data coming from satellite, and there's even further out, because the main point is we look down at the Earth, and that's how we can, that's where we are measuring. So we're not measuring a lot at our cruise altitude, we're measuring looking towards the ground, so we're looking at below us. And that gives us, with the different instruments that we have, it gives us the possibility of looking at how the pollution is moving around. That's what we mentioned with spectral cameras. We can see our larger wave spectra, so we can see different absorption rates for different gases in the atmosphere. This gives actually a better resolution than what current satellites can do, because they have to go, they are of course further out, and then there is also more noise coming out from even the tiny amount of atmosphere that is still present there. So by looking down, we can get data from below, and also what we mentioned is we get really high resolution data because we are flying lower than satellites, and we are sampling at a frequency of one Earth, so one sample per second. That gives a spatial resolution about 40 meters, which is significantly higher than what is given by satellites. So this is our improvement on the current operations.
Could I add on to that? And I'd like to add on to that as well, because what David says, indeed, looking downwards is a big part of it. And we also have some in situ measurement instruments. And how we came across the relevance of this was by looking at existing papers talking about, for instance, stratospheric ozone, stratospheric particles and their impact on the climate. And then in these papers they mentioned, for instance, that currently there's little data available. So that's also part of the relevance of this mission.
Now I want to talk about the value and the business case. I know you may be further away from me, because I represent College Aerospace, part of RTX, and we do have the largest sensor base for weather in all the aircraft that are flying in the world. And with that data, we generate the weather maps that we provide the aircraft's pilots to missions. And that is around 10, 11 kilometers, right? How will be commercial airlines your customers potentially? Will be research institutions? Will be sensor making companies? What do you see as your business value besides the sustainability and scientific value? So what is the monetary balance of the venture?
Okay, so the question is regarding the monetary balance of our mission and which potential customers we see and which markets we can operate in. Who would like to take this? Otherwise I can take it. Oh, yes?
So regarding the potential market capabilities of our product, the main goal from the beginning of this project was to develop a product that could be used for, especially for scientific purposes, so for research and for validating climate models, like David was telling. So that's our main focus. In terms of potential adaptations to markets, to turn this into a research-focused product, into more a profit-focused product, that's not something that we considered very much in depth, but eventually, for example, something that we investigated would be using the live transmission capabilities of our aircraft to, for example, survey over, let's say, survey over Schiphol Airport and understand what emissions are being generated there, if they are being carried over to the city. And that's very valuable data because it could be used for early warnings, for example. In that case, the government would be our main client.
That's a cool answer. Thank you.
We still have time for questions. Yes, please.
There's maybe not so many solar planes around there, and I believe that the Solar Impulse was one of the first ones. It came crashing down, I think, a few months ago. Did you learn something from that event, and did that impact maybe some of your design choices in a way?
So if I understand correctly, the question is how did our investigation into reference aircraft and their potential failures lead to our yes, and I believe maybe Greg. Yes.
I can, yes. Yes, so definitely it was something we looked into quite a few aircraft, both similar and also quite different. But similar in the sense of large wingspan and solar powered. So yeah, and mainly the things we implemented were related to structures and to operations, because we learned, for example, that we really have to be careful. So that was based on Helios, for example, that we really have to plan the mission very well in terms of wind shear, turbulence. That's why also taking off as early in the day as possible, for example. Yeah, and then structures-wise, of course, we had to estimate some values that we designed for, especially for the vertical wind gusts. Yeah, I think those were the main ones. Yeah.
What is limiting the endurance to 60 days?
If I can.
Oh yeah. So the question was, what's limiting the endurance to 60 days? Who wants to answer? Yeah.
It is capable of operating 60 days, but it can do longer. However, it depends also on the season where you're flying. So if the summer is over, for example, in Europe, you have to leave Europe. But our aircraft is not that fast, so then we can descend and place it somewhere else. So that's mainly the constraint for that.
I can add one. So another limiting thing, and that's based on the findings related to Airbus Zephyr, is the high ozone concentration, high in the stratosphere, also high high cosmic radiation at that altitude, which just degrades the material a lot. Also, just the fact that the solar radiation is heating the surface all the time. Another thing is any moisture that gets trapped at low altitudes then freezes when the aircraft goes higher, and that also gradually decreases the materials. So that's quite a limiting factor. And maybe as a just curiosity, I'll mention that we found a document where it was mentioned based on a conversation with one employee of Airbus that they estimated, if I'm correct, that after 6 months of using their Zephyr, the entire skin would have to be replaced because of degradation. So I think that would be one of the main factors.
Operational and maintenance related and not really endurance, because it can fly longer based on
Yes.
power and energy maybe, but there are
It
other
probably
reasons
can,
limiting
yes.
Any other burden question? Last one.
You referred to your power consumption and your power need. Was it also related to the power need of the scientific equipment, or payload?
Yeah, so the question was if the power need that we considered was also related to the payload, the scientific payload. Yeah? Yeah,
it's related, and also we need also consider like the heating power for the sensor, because some sensor cannot operate because at that altitude the temperature is around -50 degrees, and this sensor might not be suitable at that temperature, and we need also additional power for heating as well.
So what's a typical power need then?
Well,
I know it.
yeah, because I cannot really think of.
So
the
the
number.
typical power need for the payloads would be around 200 watts of power, and the overall power would fit around 6.6 kilowatts, I believe.
you are still waiting for something to come?
One last thing. One last thing which can be